To recreate the energy of a star here on Earth, you need to consign and sustain a plasma burning at over 100 million degrees Celsius. Simulating that reaction requires tracking what a million particles are doing every single billionth of a second. The scale of that math is matched by the search for pharmaceutical drugs. To map the active chemical space for a new molecular compound, you have to sort through 10 to the 60th power potential combinations. The largest supercomputers in the world cannot solve these problems. When we try to engineer nature at the atomic level, classical computing hits a hard physical wall. Classical computers run on bits, switches that are either a 1 or a 0. They process every possibility in a sequence, checking them one after the other. Looking at this diagram of drone flight paths, you can see the problem. If you want to calculate a collision-free route for a network of delivery drones, a classical computer tests the first path, then the second, and so on. As you add drones, the intersecting lines multiply into an unreadable web. This is a combinatorial explosion. Add just a few more variables to this system, and calculating that optimal route goes from taking a few seconds to taking millions of years. Because classical hardware cannot handle this scale, researchers have to rely on lossy simplifications. They artificially chop down the variables and guess the right answer by actively ignoring huge amounts of data. Brute forcing a solution with faster binary processors is a physical impossibility. We need an architecture that scales with the complexity of the problem itself. That architecture runs on the quantum bit, or qubit. Unlike a classical switch stuck at a 1 or a 0, a qubit leverages a physical property called superposition. It can hold the states of both 0 and 1 simultaneously. As this animation shows, scaling this up creates a massive mathematical advantage. 2 qubits manipulate 4 states at once. 3 qubits handle 8. If you have n qubits, you process 2 to the power of n states simultaneously. By scaling up qubits, you build a computational workspace large enough to hold an entire combinatorial explosion of possibilities at the exact same time. Qubits also link together through a property called entanglement. When 2 qubits are entangled, the physical state of one becomes permanently bound to the state of another. Programmers use this property to directly correlate distant, complex variables without having to calculate the intermediate logic steps connecting them. In financial optimization, for example, a macro-level economic risk like the unemployment rate can be directly entangled to the default rate of a specific loan portfolio. Instead of running thousands of separate market simulations, entanglement allows us to hardwire complex systemic relationships directly into the physical hardware of the computer. But holding millions of possibilities at once is useless if observing the computer forces it to collapse into a random guess. You still need a way to extract the right answer. The solution is interference. This is the secret physical mechanic driving operations like Shor's and Grover's algorithms. Looking at this model of wave interference, you can see how it works. When algorithms are intelligently designed, incorrect answers become completely out of phase and destructively cancel each other out. The correct answers align perfectly to constructively amplify into a massive peak. Returning to our drone flight paths, a quantum algorithm does not test every single route one by one. It uses destructive interference to mathematically erase the routes that result in a crash, leaving only a single, clean, optimal route behind. Through the precise alignment of waves, a quantum algorithm sculpts probability until the optimal solution is the only one left standing. Translating this math into physical hardware is incredibly difficult. Current quantum systems are fragile and highly susceptible to environmental noise. A minor temperature fluctuation or a stray electromagnetic wave can cause a qubit to prematurely collapse out of its quantum state, destroying the calculation. To keep the system stable, engineers are currently relying on a technique called mid-circuit measurement. This uses secondary helper nodes called ancilla qubits alongside the main data qubits. These ancilla qubits act as a diagnostic tool. They interact with the primary qubits, allowing scientists to detect errors and correct them on the fly without ever looking at and destroying the primary quantum state. Overcoming this noise to achieve stable fault tolerance is the primary focus of computer science today. While fault-tolerant machines are years away, The first demonstrations of quantum advantage will signal our transition from guessing at nature's complexity to calculating it with precision. It is the hardware required to master fusion energy on Earth, to secure global networks with unbreakable cryptography, and to perfectly optimize planetary supply chains. As the physicist Richard Feynman pointed out decades ago, nature itself is quantum. To simulate it, you have to use a quantum system. We are building machines that natively speak the language of the universe, removing the need to translate quantum reality into a rigid binary code.